Hi, my name is Mela Coffey, and I'm presenting our paper, Reactive and Safe Co-Navigation with Haptic Guidance. So we consider co-navigation to be when a human is operating a robot and the human and robot work together to reach the same goal. So here the human is responsible for making high-level decisions and gets the final steering command, and in turn the robot, which may have sensing capabilities, provides collision avoidance and route suggestions via haptic feedback. So we envision two applications for this co-navigation, one being the operation of powered wheelchairs and the other being teleoperation through a remote environment. And there has been a lot of work related to haptics-aided navigation, and these are just a few highlights on this slide. On the left, for collision avoidance, we generate a force feedback away from obstacles, and these don't tell you how to get around obstacles, however. We also have studies like in the middle that use haptic feedback to guide a user along a path where the force increases as the user deviates away from the path. And on the right, we have a combination of some sort of collision avoidance plus guidance to a target. In our work, we want to guarantee collision avoidance and provide intuitive haptic feedback. So the goal of our work is to guide the user along the path while guaranteeing safety. And we propose to use a control the up and off function for guidance and a control barrier function for safety. So on the right is an overview of our algorithm, which I'll walk through as we go, but let's just start with computing what we call a temporary goal. Now, before we can even start the algorithm, we have to generate an optimal path, and we use a non-holonomic ROT start algorithm to generate the tree from the final goal to the start position. If the user deviates from the optimal path, the black dashed path in this case, we have other path options that lead to the goal as well. So to compute the temporary goal, as the human navigates the robot, we compute the distance from the robot to the optimal path. And if the user is farther than some distance Dmax, then we assume that the user is rejecting that optimal path. And in this case, we would update the optimal path to the nearest branch in the stored tree, this pink dashed line here. Then we would get the nearest node on the path. And once we have that node, then the temporary goal is defined as n steps ahead of that node I near. Now that we have that temporary goal, we can compute the force that pushes the robot toward the temporary goal and ultimately along the path. And this is where the control Lyapunov function comes in. So CLF controller overall serves to drive some Lyapunov function v of x to 0. And since we want the force to drive the robot to the temporary goal, we let the CLF be the squared Euclidean distance between the robot and the temporary goal. And then we can solve for the CLF control input by solving this optimization problem at the bottom. And this ultimately results in a force that helps steer the robot toward the temporary goal. So now we need to make sure that the CLF input is safe, which is where the control barrier function comes in. So note that the ROT star planar doesn't actually account for small or dynamic obstacles. So if there is a dynamic obstacle that moves into the path, for example, then we need a force that will push the robot around that obstacle. So here we build on our previous work where we use a CBF controller for safety. Here, the CBF controller lets us compute a safe input that's as close as possible to UCLF, the CLF guidance force, while being safe. A CBF controller ensures that some function hi of x is always greater than or equal to 0, and we can define one CBF for each circular obstacle as such, so that the safe set is all of the points outside of this safe radius. Finally, we compute the force feedback as the difference between the safe CBF input and the user steering command, and we also allow the user full control over the robot. So here's a simulation we've carried out with the virtual pilot and a dynamic obstacle. Here, the temporary goal is this red dot, and it's computed along the black reference path. And we assume an agreeable virtual pilot, and we see that the CBF is what's pushing the user around the obstacle, that dynamic yellow obstacle. We also conducted human pilot demonstrations within agreeable humans. So here we just want to see how well the human can follow this black optimal path over here. So here the human has a first-person point of view of the environment and operates a Geomagic Touch haptic device to steer the robot. Here the robot is aware of all of the orange cones and sends force feedback to the human through the haptic device. And we can see that the human is able to follow the black reference path in all cases. We also introduce a situation in which the human and robot disagree. So here the robot only knows about the cones, but not the dogs. Originally, the robot generates this black dashed path here, which would collide with one of the dogs. And as the human approaches the dogs, it rejects the original path. And once the robot realizes this, it then switches its suggested path to this black dotted path. After the switch, there's minimal disagreement. Thanks so much for your attention, and feel free to contact me with any questions.